Okay, so a couple of things off the top. So I've got most of the corrections done. I had a handful that people put in my office when I wasn't there. So I'll get through those pretty quickly this afternoon. And then I'll get grades updated. So currently, if you're looking at this, I had one or two people reach out. Don't freak out. It's the number of problems you got correct that you reworked. So if you see like a 5, that means you reworked 5 of the problems correctly. So this afternoon, what I'll do is I'll take that number that you got correct, and basically you're getting half the points back. So multiply it by 2.5 points, right? So I'll get something up there that shows you the number of points that you got back from your corrections. Currently, the way it's showing is it's just the number of questions you reworked correctly. Right? So I'll get what look like new assignments that'll be up here, which will just be like exam 2 correction points, and then exam 2 grade with corrections. So the one will show you how many points you got on the corrections, and then the other is what your grade is with those points added in. Okay, so you'll see those pop up this afternoon as I finalize kind of going through finishing up grading those last handful of corrections that were turned in. Then from there, I'll also put up what look like 2 new assignments. It'll say lowest and highest exam grade. And then those will be the ones that actually get weighted by the 30 and 20%, right? Because some people, it'll still be that exam 1 was their highest grade. Some people it'll be exam 2 with the corrections was their highest grade. So I still want you to be able to see what your original exam scores were. So those will be left up there, but the ones that will actually be weighted and kind of factoring into your grade will be that highest and lowest exam grade that pop up there this afternoon. Okay. So as I'm working on this afternoon, don't worry about, there'll be some intermediate stuff. Don't worry about the grades this afternoon. After 5 o'clock today, if you have questions about grades, feel free to reach out to me after that. But this afternoon, I'll probably, there'll be a certain time frame where I'm kind of uploading things and making sure that I'm getting things ironed out so you can see exactly what your current grade is at. Okay. So you'll see those pop up there this afternoon. Another thing I want to mention is notice like anything that I leave up here in assignments should be counting for 0% of your total grade, right? Everything else, I think right now kind of has a factor in. So later today, I'll be creating like a new category that's exam raw scores or something. So you can still see your exam 1 and 2 grade, but then the highest and lowest exam grade will be the assignments that get posted up there that actually count, right? So I'm able to identify what your highest and your lowest exam score were or was. So if I go to student view here, one thing that you make sure you have selected, if I go to grades, make sure that this is calculated based only on graded assignments, right? So if you don't have this selected, it might kind of be factoring in some of these things that aren't being factored into your grade, right? Like I'll have exam 1 and 2 up there, but the actual thing used to calculate your grade is your lowest and highest exam score that will be showing up on campus. Okay. Like I said, once I've kind of finalized things after 5 o'clock today, if you have any questions or need anything clarified, please let me know. I'll probably put an announcement up there that kind of gives a better description of what you're seeing on Canvas as well. But try to hold off on that until after this afternoon. I get everything graded and everything updated. Okay. Overall, great job on the corrections. Like people that turned them in did for the most part, did a very, very good job. I think it's a useful tool that helps you, go back at least from the work that you did, unless I guess you cheated and someone did it for you. But like, I saw a lot of people, I think that it probably helped them realize why they did what they did wrong. I saw some people even mentioning stuff about critical values, which was stuff after we did the exam, but it was still connected to what we did in the exam. So people were kind of making that connection. So overall, very happy with that. The average should be right around a 75, maybe even a little bit higher for this section, I think, after I get all those corrections factored in. So good job on those. Okay. So before I forget, and by the time we're in class, one thing you'll also see get posted up there, I'll probably put up the next Connect assignment, just so you can start working through it. So after we get done with today's class, you can do confidence intervals for sample mean differences, sample proportion differences. Some of the questions on there we haven't have worked through yet, but I just want to get it up there early so you can start kind of chipping away at it. I also had that additional video that I posted in replacement of Friday's class. So we're starting today. I'm kind of assuming that you watched it. although I will go through a little bit of a review, kind of mentioning some of the things that I mentioned in that video, because I'm not that optimistic that I think everybody got on and watched that, right? So what that video was covering was we left off Wednesday. We're looking at the difference in sample means and building a confidence interval for where the true difference in the population means were. So what I did on that video was think about, okay, we're going to do hypothesis testing when we looked at the difference in sample means. Okay? So how do we construct that test statistic? Everything else in terms of hypothesis testing, exactly the same as what we did when we only had one sample mean. Okay? All these steps, looking up critical values, looking up p-values, everything's exactly the same. The only thing that changes is our test statistic equation. So when we only had one mean, we were going to take the sample mean that we found, subtract the assumed true value of that mean, and then here we were dividing by that standard deviation of the statistic we were interested in, or the standard deviation of our sample mean. So it looks something like this. Okay. Well, when we did confidence intervals for the difference in sample means, this was the equation that we were using, where we said that standard deviation of the difference in sample means was really just taking each sample means variance, adding them together. That gave us the variance of the difference in the sample means. Well, we wanted the standard deviation, so we then had to just take the square root. So we're going to do the exact same thing really with our test statistic equation. We're going to look at the statistic we're interested in is no longer just the sample mean, but it's going to be the difference in our sample means. You can kind of think about this as almost like our sample difference. The difference in our sample means is kind of like a sample difference that we found. We'll then subtract. So before we subtracted the assumed true value of the population statistic. So now if we're thinking about the sample difference, we're going to have an assumed true difference. Okay. And then here, we're going to divide by the standard deviation of the statistic we're interested in, just like we did, before. It's just now we know that that standard deviation has a slightly more complicated formula where we have to take the square root of each group's population variance over that group's sample size. So we're still following the same kind of principles, right? Take the statistic you're interested in, subtract the assumed true difference of that statistic, divide by the standard deviation of that statistic. It's just that to find the standard deviation, we got a few more moving parts now. Okay. Any questions on this? So this is where we left off Wednesday. I went over some examples of this in the video I posted on Friday. I also put up some accompanying Excel work with that. We won't do anything in Excel today, but Wednesday we'll take a look at that again. And kind of open that up and then kind of see how we do hypothesis testing and confidence intervals for two population proportion examples, which is what we'll do today eventually. Okay. So that was our setup. But once we found our test statistic, like I said, finding critical values, finding the p-value, what type of tailed test, everything's exactly the same. Now, one thing I also mentioned in that video is I'm always going to use assumed true differences of 0 here. So why am I going to do that? Well, I'm doing it in truth to make it a little bit easier as we kind of work through some of these examples. I think Wednesday I'll show you what happens if we don't use an assumed true difference of 0. But you can kind of imagine, like, if I'm thinking about this difference between population means, it doesn't seem that crazy that I would want to know, okay, is that difference greater than 0, right? I'll assume the opposite is true, which is that's less than or equal. So I'm using this assumed true difference of 0 here. Well, that is going to be something that makes a lot of sense, because if I'm wanting to test for whether or not that difference is greater than 0, what I'm really saying is, does group 1 have a greater mean than group 2? Well, that seems like something you're going to want to test for a lot. Like, is the population mean, or the units I produced under one production method greater than the number of units I created on average from this other production method? Or, is I don't know, did my one section have a higher exam score than my other section, right? If I just have samples of the two. Today we'll do the proportions. So the proportion of people who own a gun go up or down over these two time periods, or the proportion of people who were in favor of a certain candidate, right? Does that vary between state A and state B, right? So that's a very reasonable kind of difference that we would be looking for. You can kind of imagine the other ones, you know, less than 0. What I'm really saying there, that group 1 has a lower mean than group 2. And then if I have, is it equal to 0? Or sorry, not equal to 0. What I'm really saying is, are these two groups, do they just have different means? They're not the same value, right? So using this assumed true difference of 0, it's quite often going to be the test that we want to do anyways. It just makes it a little bit easier for right now. We can use values other than 0, but I'm not going to expect you to do that like on the exam, on the final. I might put like one question on the homework, connect homework, where we use something that's not 0, but for the most part, always kind of using this assumed true difference of 0 for this class. I'll show you an example here and there for what would happen outside of this class. But for now, you can use that assumed true difference of 0. Okay. All right. So the next step, so that's kind of a little bit of review of what was in that video. So what we're going to do or focus on today is looking at the difference between two sample proportions. Now, proportions are just unique versions of sample means. But if we go back and remember, okay, let's say I've got my first group's sample proportion. It should be normally distributed around whatever that true population proportion is. And then the variance of my sample proportions, well, usually we would use the population proportion, but we don't know what that is. So the best guess or the best estimate we have is our sample proportion. So we said we would take our sample proportion times 1 minus that, and then divide by our sample size. And that's going back to one population stuff. And I would have the exact same thing would be true for my second population or my second group. I would just be using their sample proportion and sample size to determine the variance of that sample proportion. So what we're going to do first is try to figure out, okay, can I do confidence intervals for what the true difference in population proportions is? Well, yeah. First of all, I'll center it around the sample difference that I find. So now instead of the difference in sample means, I've got the difference in my sample proportions. I then add and subtract my margin of error to get my lower and upper bound. And what is my margin of error composed of? Well, it's the number of standard deviations away that I need to go to get alpha over 2 on each side of my confidence interval. So I, just like when I knew the population variances, I get to keep using that standard normal or the Z table. I'm then going to multiply this by, this is the number of standard deviations away I need to go. The actual value that I want to add and subtract to my sample difference would be the standard deviation of the difference in my sample proportions times the number of standard deviations away I need to go. Well, here, just like with sample means, so with our sample means, we said, okay, how do I get the standard deviation? Well, I take the square root of each sample means variance added together. So same thing with sample proportions. I'll take each group's variance, add them together, and then to get the standard deviation, I need to take the square root. Excuse me. So it's following the same format. It's just now, instead of the variance of my sample means, I'm using the variance of my sample proportions. Okay. But at this point, the steps are kind of the same. I identify my sample proportions and my sample sizes. Also, this should be N2. I'll plug everything in that I was given. And then the only thing left that I need to do is look up that Z value. Okay. Any questions there or confusion or can't read my writing, anything here? Okay with this up to this point? So let's put some actual values to this. So scroll down here. This is all just, I find p-values and critical values the same for hypothesis testing. We had that test statistic for the sample means, but now we're looking at, where was I? There we go. The difference in sample and two population proportions, right? So we'll use our sample proportions as the best estimate, build our confidence interval around that. And then here, this equation would give us our margin of error, right? The thing that we add and subtract to get our lower and upper bound. Okay. So steps, identify the two sample proportions, sample sizes, where alpha is, look up that Z value, and then it's just a matter of plugging things in. Okay. So let's put some actual numbers to this. Let's say I had a survey that was given in 2 different years. Okay. So I've got 2011 and 2010, and I want to know what's the 99% confidence interval for the true difference in proportion of people who favored healthcare coverage for everybody. Right? So 607 people in 2011, 600 people in 2010, and I want to build this 99% confidence interval. So let's go here. We'll think about what my group 1 and my group 2 are. Well, I think we had the sample proportion in 2011 was 0.84, where 84% of people were in favor of healthcare coverage for everyone. In 2010, it was only 82%, or a proportion of 0.82. Let's see if I think this was 607, and then the sample size, number of people in 2010 that they had in the survey was 600. Okay. If I wanted the 99% confidence interval, what's my alpha value? Yeah, 0.01, 1% outside the interval in decimal form. So here, my group 1, whenever you have like a time example, your newest time period will always be your first group. Because like if I said that proportions increased over time, well, then I'm thinking about positive values for the difference, right? If I set it up the other way where I did like 2010 minus 2011, well, then if the proportion went up, I'd actually have a negative difference. It just doesn't line up with kind of how we just talk about things in English. So it's easy to think about, always put your newest time period first. So we would do what? 0.84 is that group 1 minus 0.82. That's my group 2, is from 2010. Put the newest time period. So if we're doing with years, 2011 would be first. If I'm looking at the differences in like months and I wanted to go from, I don't know, August to September, September would be the first group. Always put like the most recent time period as that first group. Yep. So this sample difference that I found is 0.02. I'm going to base my confidence interval around that, right? So I'm basing my confidence interval around that. So if I looked at the possible answers here, 0.02 should be exactly in the middle of all my confidence intervals if they were all possible. Here, 0.02 isn't even in my confidence interval for C, so C I can rule out right away. The other 3, it looks like 0.02 is kind of right in the middle of all of them. So I got to finish the rest of this. So I'm going to just plug in what I know first. So this is what? 0.84 times 1 minus 0.84 over 607. And then add to that the other sample proportion times 1 minus that sample proportion over that group's sample size. So when you're doing this calculation, a lot of the times, like doing this in parts, like find what this value is. That way you only have, one value to plug in here, right? As opposed to like doing all of this on one line. Make it a little bit easier by breaking it down into parts. So the only thing left I need to do is look up this Z value, right? So it's going to be the Z value that gives me that desired alpha over 2 in each tail. So what I'm doing is looking for, or I should say, an alpha total outside of my interval. So I want the Z value that gives me alpha total outside my interval or in the tails, which I've got a side on each, there's 2 sides of my confidence interval. So on each side, there will be alpha over 2, or in this case, 0.005. So that's the area that I'm going to want in each tail, and I want to find the corresponding Z value or number of standard deviations where I need to go in order to get that. So remember, I'm doing confidence intervals here. So I'm building an upper and lower bound. I'm always going to have a side on each side of my confidence interval. So for a confidence interval, it looks very much like a 2-tailed test. So finding critical values for a 2-tailed test will be exactly like finding this Z value for confidence. Those 2 things are closely related. Yeah. Oh, what did I do wrong here? Yeah, because I didn't write this down right. Sorry. This is 0.01, right? If we go back to our original alpha. I knew the number and I wrote down the wrong one. So I don't know how that explained that. But so we've got 0.01 was our alpha. So when I divide that by 2, I got 0.005. Thank you for asking that. So I'm going to go to my Z table. I'm going to try to find the value that's closest to 0.005. So I look here, looks like it's in between these two. So negative 2.57, 2.58. I'll use the higher of the two. Now remember, I just found negative 2.58 because I was looking at the left side of the distribution, 0.005. When I looked it up in the table, I'm looking up the area in the left tail. Well, I'm going to go that same number of standard deviations away to the right to get my upper bound. So this positive and negative sign are really already built into my confidence interval equation. So I just need to plug in that 2.58 there. And now I just add my margin of error to this sample difference to get my upper bound. I subtract to get my lower bound. And it's just a matter of computation at this point and being able to get entered into my calculator. Like I said, one thing that can help is maybe calculate this first, and you'll have one value that you can plug in there, and it makes the, getting this entered into your calculator at one time a little bit easier. Okay. Any questions over any of those steps up to this point? Okay. So I use the Z table, like we should be, to find this value. Right? There's a shortcut, and I've mentioned this before, but I just want to keep pointing it out, that you can use, which is if I use these T tables, if I go down to the very last row, remember this infinite degrees of freedom really represented the standard normal distribution, because we never can truly get an infinite degrees of freedom, but if we could, our student T would converge to a standard normal. So we can also use the last row of our student T distribution to look up Z values. If I wanted the area of 0.005 in that tail, I can actually be a little bit more precise. Instead of 2.58, I can go out to that third decimal, 2.576. So I point that out because I believe that's the value that I was using on the slides. That if you use that last row of the student T table, you can actually get it out to that third decimal, which is, I believe, what I was using right here. So it's almost like the student T table has that last row. It kind of incorporates a couple of the most frequently used Z values in there. And, coincidentally, right, those are going to often be values that we want to use in our confidence intervals or in our hypothesis testing. Okay. Any other questions on this before we move on? So I want to make a point here. So I had what? Negative 0.036, 0.076. So this is my lower bound and my upper bound. So what I'm really saying is with 99% confidence, the true difference in proportion of people who were in favor of healthcare coverage for everyone, the difference from 2011 to 2010, it could be a positive value, which would imply what? More people were in favor of it, or the proportion was higher in 2011. But it also could be that difference is a negative value, which would imply that the proportion was actually higher, or more people were in favor of it in 2010. Or it could be that the true difference is actually 0, which would mean that the proportions between the 2 years would be exactly the same. So this confidence interval doesn't really allow me to say much. With 99% confidence, I can't really make any statements here because the true difference could be positive, could be negative. It could even be that it hasn't changed at all. That difference is 0. So this is where confidence intervals, it's just the way the data is. We didn't find sample evidence that was strong enough to be able to say that it was only positive values or only negative values. Now the sample difference we found was what, 0.02. So we did find sample evidence that, the proportion has increased over time, but we can't really say that it's any different from 0, or we can't say that, it couldn't be negative at the 99% level based off this confidence interval. Okay. Any questions about that interpretation? It's another way I want to say that. think that's all I want to say here. Oh, no, I want to show you something. I knew there was something else that I wanted to point out. So even though we found sample evidence, right, the sample difference we found was 0.84 minus 0.82, so 0.02. It looked like things went up. The reason why our confidence interval still includes positive and negative values is because based off of our sample sizes, there must have been a significant overlap when we were looking at the distribution of sample proportions. So even though we found a sample proportion difference that was 0.02, it could have been because even though the true population proportion was actually lower in 2011, we could have just so happened to see a sample proportion from the right side of the distribution in 2011 and a sample proportion from 2010 that happened to be lower than whatever the true population proportion is. So even though we found a sample difference that was positive, it still very well could be the case that the actual difference, right, 2011 minus 2010 could be negative. But if it had only included positive values in our confidence interval, well, then we could have said that we know this isn't the case, that with 99% confidence, it must be that the true population proportion in 2011 was higher. But based off the sample evidence we found, we can't say that. So can't really say a whole lot there. I have this other example, and I'm going to go really quickly through it because I didn't so much have it to like work through it completely. If you want to work through it on your own and make sure you can recreate the numbers, that would be maybe a good idea. But I'm more so putting here to point out a couple things and maybe think about how these examples change. So going from this example, let's say we have the same survey, so same sample sizes, same years, but now I ask people, are you in favor of the Affordable Health Care Act? Right? So in 2011, 51% of people were, in 2010, 48% of people were. And I still want to build a 99% confidence interval for the difference in the proportion across these two time periods of people who are in favor of the Affordable Health Care Act. So first of all, my confidence interval equation, everything's going to be the same. So I'll plug in my sample sizes just like I did before. Now, instead of 0.84 and 0.82, my sample proportions will be 0.51 and 0.48. So I found slightly stronger evidence, right? A sample difference that was a little bit larger here. It was 0.03. And when I'm looking up that Z value, or the number of standard deviations away I need to go to get alpha over 2 on either side of my confidence interval, well, at the 99% confidence interval, alpha is going to be 0.01. That's what it was in the previous problem. If I divide that by 2, it's going to be 0.005. So when I look that value up in my table, I'm going to get the exact same Z value I did before. Anytime we're building a 99% confidence interval, when we can use that standard normal distribution, we're always going to find the same Z value for our confidence interval. Okay. So it's this 2.58 or 2.576 will start popping up a lot. Okay. So from here, it's just a matter of really getting everything plugged in. It's going to look very, very similar. It's just my sample proportions are different now. I'm using the same Z value because I'm building the same level of confidence, and my sample sizes were the same as well. So it'd be pretty easy to set this one up and look to see, okay, is the true difference here in the unfavorability of the Affordable Health Care Act, has it become more unfavorable or less unfavorable? Well, we can't really say, right? Because we, once again, have negative and positive values there. So once again, not a whole lot can be gathered from this survey. But there is one thing that's kind of interesting. I wanted to use this to connect to some things we talked about in the past about bias that exists when you're collecting data. So notice when they asked people, are you in favor, stop, oh my gosh, come on, there we go, of healthcare coverage for everyone? Across two time periods, like about 84 and 82% of people were in favor of that, right? But when they asked them if they were in favor of the Affordable Health Care Act, 51 and 48% were actually against it, right? Had unfavorable views of it. Now, they're not synonymous, but the primary goal of the Affordable Health Care Act was to ensure healthcare coverage for everyone. So this is a really good example of seeing how you frame the question. You can elicit very different sample evidence. right? So especially when it comes to like political things, if you use the names of policies where people can like, oh, I'm supposed to hate that bill, or I know about that. You can get wildly different support for different policies by using the names. While if you use the actual, like what the bill or what the policy is actually trying to do, a lot more people may be in favor of it, or vice versa, but you can get very different results. Right? So I thought it was kind of interesting. That's why I like this survey. And if you wanted to, you could do like, well, was there a difference in 2011 between the proportion of people who favored healthcare coverage for everyone and the proportion of people who were in favor of the Affordable Health Care Act? And there, you will only see positive out. Right? You're going to find a significant difference there if you do that. But that's a little bit of an aside, but I always kind of like to mention that there. And really gives you another example to kind of make sure you can get this entered into your calculator. Like I said, finding this first and then plugging one value in might make it a little bit easier. Okay. All right. Any questions on that before we kind of tackle the last thing for today, which is hypothesis testing with sample proportions. So, kind of remind you what we did earlier. When we were looking at test statistics, we said this was the equation for the test statistic for the difference in two sample means. Okay. We're going to do a similar thing now and try to come up with a test statistic for the difference in sample proportions. Well, we always start out, the test statistic is always telling us the number of standard deviations away from the assumed true value our sample evidence was. So now, instead of looking at this sample difference for the difference in sample means, we've got a difference in sample proportions, right? That's our sample difference now. We'll subtract the assumed true difference. I'm still going to keep this as 0, make our life a little bit easier for now. But then now we divide by the standard deviation of my difference in sample proportions. Now we might think we can just grab that from the confidence interval equation. And unfortunately, it doesn't quite work out to be that way. We could, if we had the exact same sample sizes, we could actually use that. But we want to make sure that we have a format that works no matter what question, what we're tackling, right? If we have two samples, or two populations with different sample sizes, we want to make sure we have an equation that works for that scenario as well. So one that is universally works no matter what our sample sizes are from the two groups is going to be to take the square root of, and the way that we would determine the variance is using this thing called P bar, which I'll write down what that is here in just a second, times 1 minus P bar, and then times the sum of 1 over each group's sample size. So using this formula guarantees that what we're calculating will come from a standard normal, or represents the number of standard deviations away from a standard normal distribution. Now, the reason why it's a little bit different than what we're doing with confidence intervals, I'll show you in just a second. But P bar here looks something like this. Excuse me. And really what P bar represents is you're taking the number of people, for instance, who were in favor of Affordable Health Care Act in 2011, plus the number of people in 2010, divided by the total number of people. You're getting like an average proportion over the two groups. So over the two time periods, or if we have groups here, over the two groups. Now, the reason why we are doing that is because, so this is are there any questions over anything I wrote down here? Hopefully everything's clear, but I want to give you a little bit of an insight as to why we have to use this equation as opposed to the one we were using for confidence intervals. So with confidence intervals, we didn't have any assumed true values. With hypothesis testing, we have an assumed true value or assumed true difference. It's 0, but it's still, we're assuming that it's 0, right? Well, the problem is, let's say I assume that that difference is equal to 0. What are some values for my sample proportions that would actually support that? Well, they could both be 0.5. They could both be 0.3, 0.9. I'm not actually saying anything about the assumed true values of the population or of the sample proportions or the population portions. I'm only saying something about the assumed true difference. Well, the problem is, if we go back, we're thinking about confidence intervals for this, the variance of each sample proportion will depend on what the actual value of the population proportion was from those two groups. But we don't have that. We don't even have an assumed true population proportion. We just have an assumed true difference. So we're going to have to use our sample proportions to come up with the best guess of what our best guess of where the population proportion actually is. So then we're going to take kind of like the average across the two. Using that average or that p-bar, we're going to weight it by 1 over what each group sample size was. Also, sorry, this looks like I'm multiplying. This should be a plus in between those two. And now if we do it this way, this guarantees that when we're calculating the number of standard deviations away that we need to go, we're using the correct standard deviation for the difference in sample proportions, and that this value will come from that standard normal or the z-tables. Okay. But really, I mean, the test statistics is just a matter of plugging in our values. Like once we have our sample proportions, we're always going to have an assumed true difference of 0 in these examples. Plug in our sample sizes and our sample proportions. It's going to be a matter of computation. And the process of hypothesis testing looks exactly the same, other than we have a difference in our test statistical equation. But finding critical values, p-values, nothing has changed. So that's what this slide has here, kind of what I just had written down. Steps are going to be exactly the same. In fact, they don't look any different from what we were doing with two population examples. It's just calculating that test statistic that'll look a little bit different. Okay. So let's put some numbers to this. So I have this another political example. We're looking at the proportion of people who are going to vote for Biden and Trump in 2020. And we had this huge poll. So the first thing I want to do is I'm going to figure out what my null alternative hypotheses are. So I want to test for whether or not Biden will receive more votes than Trump, right? So it gets a little bit tricky sometimes with identifying the null alternative hypothesis, but just write down what we were told. So really what we want to test for, or alternative hypothesis, was that the proportion of people who were going to vote for Biden is greater than the proportion of people who are going to vote for Trump, right? Maybe we're trying to predict the election. Well, the problem is this isn't written down in terms of the difference. And the difference that we have would be, right, Biden minus proportion for Biden minus the proportion for Trump. Biden, I'm just using subscript B and T, subscript T. So this is like my group 1 and group 2 here. So how can I rearrange this so that I have my alternative hypothesis as using this difference variable? Well, saying that the proportion of people who vote for Biden is greater than Trump is really saying that the difference between the two would be positive, right? And I could think about, really, I'm just subtracting this from both sides. And then that represents my difference. So I've got, if I want to know if the proportion of people who are going to vote for Biden is greater, I'm saying that difference, I want to test for whether or not it's greater than 0, which means I'll assume the opposite is true for my null hypothesis. You kind of see where that's coming from. So like the way that it usually it'll read is you're trying to see is one group greater than another group. Well, what that's really saying then is that difference going to be positive. Once I identify my alternative, the null is just the exact opposite of that, right? Stacking the deck against myself. Any questions on this? What if I just wanted to know, is the proportion of people who are going to vote for Biden different than the proportion of people who are going to vote for Trump? What would my alternative hypothesis be there? Is that difference so if I'm saying, is the proportion of people who are going to vote for Biden different than or not equal to the proportion of people who are going to vote for Trump, what I'm really saying is that difference anything other than 0? Right? Because in order for that to be true, it would have to be that the difference is not equal to 0. But that's not what we're doing. Just as a hypothetical, we had this outline. So what type of tailed test do we have? Got a greater than sign in my alternative hypothesis. So I've got a right tailed test. Okay. So what I'm trying to do is I've got this distribution for the difference in my sample proportions. And it's going to be centered around the true difference, but I don't know what that is. I just have an assumed true difference of 0. I found sample evidence. I think it was 0.49 or 49% of people were going to vote for Biden, 49 for Biden, 47 for Trump. So I think the sample difference that we found here was 0.02. My p-value, or the probability that I saw the sample evidence that I did that was as inconsistent with what I assumed to be true, or something even more inconsistent, that area to the right represents my p-value. Okay. How can I find that? Well, I'm going to turn this sample difference that I found into a test statistic, or in this case, a z statistic, because it comes from a standard normal distribution. And then I can use that to find the area to the right by using my z tables. Okay. Well, how do I do that? Well, that's where I go, excuse me, back to my test statistic equation. I'll have my sample proportion of people who are going to vote for Trump and Biden. I'll have my sample size for both groups, and that's just a matter of plugging everything in. So I think here, the sample proportion of people who are going to vote for Biden was 0.49. Sample proportion of people who vote for Trump, 0.47. And then we're using the same 1,500 people, so the sample sizes of both groups are exactly the same. So I'll have this assumed true difference of 0. From there, I'll skip ahead a little bit. It's just going to be a matter of, okay, figure out p-bar. So plug in my sample sizes of 1,500, plug in my sample proportions of 0.49 and 0.47. I end up getting 0.48. So when I have sample sizes that are exactly the same, remember I said p-bar kind of represents like the average proportion across both groups, or in this case, both, Biden and Trump. But if I have the same sample size, then the average is really just going to be the midpoint between whatever those two sample proportions is, right? They're both kind of being weighted equally. So if we had different sample sizes, then we might get a not so intuitive result, right? One of them is going to be weighted a little bit more because it had a higher sample size than the other. But here, when the sample sizes were exactly the same, it's really just the midpoint, right? It's like the average proportion across these two groups. So we'll use that p-bar of 0.48. We've got our two sample sizes, our two sample proportions. Just a matter of plugging those into that test statistic equation, which, coming up to the final, you'll have that in front of you on the formula sheet. And a matter of getting this entered into our calculator. Once again, maybe finding the denominator first might make it a little bit easier, but we get about 1.097. Okay. So my test statistic here is 1.097. So if I use my standard normal table and I look up, I can't look up 1.097, I have to round this to the second decimal. So 1.10, I guess, if I round to the second decimal. But when I look it up in the table will tell me the area to the left. I wanted the area to the right for this right-tailed test, so I need to do what? Subtract it from 1. So we'll look up that 1.1 on our Z table. That was our test statistic. Scroll down here. 1.10, 0.8643. So that's the area to the left of our test statistic. Excuse me, approximately, right? I do a little bit of rounding here, so I'm not using Excel. Well, I had to subtract that from 1 to get the area to the right, which is what I wanted, which is my p-value. So we just found our p-value to be 0.1359. I then want to compare that to alpha. If it's less than alpha, I'm going to reject. If it's not, I fail to reject. Now, one thing to think about here, what this kind of represents, is I'm really checking to see, is the probability of what I saw, right? The probability that I saw what I did for my sample, if what I assume to be true was in fact true, if that goes above this threshold probability I've set, alpha, or the threshold type 1 errors I want to make, then I'm not okay rejecting the null. So here, is my p-value going to be less than alpha at any of these levels? It's not less than any of these, right? 0.13 is actually greater than all of these. So I'm going to fail to reject the null at every single level. So this kind of shows, like, even with 1,500 people, it's really hard to predict elections. Like, there was a difference of 0.02. I mean, if you look at the popular vote, it's not usually separated by more than a couple percentage points. So even finding sample evidence that's like 3 or 2 percentage points off doesn't really give me enough statistical power, even with 1,500 people, to be able to reject the null, right? And the null here was that the difference was less than or equal to 0, which would imply that Trump is going to get a higher proportion of the votes, right? So this kind of highlights, like, it's pretty hard to be able to make these predictions when we're dealing with the difference in proportions. So we really got to like get big sample sizes, which the internet makes a lot easier to do, right? When we're trying to do political polling stuff. Okay. Any questions over this? I got one more thing that I want to go through. Excuse me. Okay. So we've got our p-value rejection decision. What if I wanted to look at critical values? So here, I think on the slide, it says what's, use the 99% level. So we're going to use an alpha of 0.01. Okay. So what I'm trying to do with critical values is find this z value that gives me alpha total in my right tail. Well, this gets a little bit tricky because when I go to the table always has the area to the left, right? So I would actually need to look up what? 1 minus 0.01 or 0.99, which I can do that. Or I could remember, well, if I look up 0.01, that'll be like looking up 0.01 in the left tail. I'll find the same value. It'll just be negative, right? Because this is a symmetric distribution. So I can look it up both ways. Excuse me. So if I looked up 0.99, looks like I'm in between these two values. So 2.32 and 2.33. So 2.33 would be my critical value. Or I could have just looked up alpha, right? So where's alpha? 0.01. So it looks like I'm in between these two. Negative 2.32 and negative 2.33. And then just remembered, oh yeah, that's the left tail. I'm looking at the right tail. So it's negative 2.33, but positive. Or I could have just looked up the area to the left, which is 0.99. That way I would have just found the 2.33. Either way, though, you can get to the same result. You should also remember when we're doing right tail tests, we said critical values should always be positive, because if that standard normal distribution is centered at 0, the right side will always be positive values. So here's my rejection region. I'm then going to plot my test statistic to see, okay, is this test statistic in my rejection region? Well, 1.097 was that test statistic. It's not going to be in that rejection region, right? The visual is pretty easy to see. We should not reject here. But if we want to remember what the rule was, if my critical value was less than the absolute value of my test statistic, that's where I said I was okay rejecting. Well, here my critical value is 2.33, my test statistic 1.097. That's not going to be less than my critical value, so I would fail to reject with the critical value approach as well, which lines up with the rejection decision that we had using the p-value approach. So it doesn't matter which approach we use, we should end up with making the same rejection decision. Yeah, any questions on that? I went through that a little bit quick here. Okay. So on Wednesday, we'll look at how we do the difference in proportions, and I'll show you how you do confidence intervals and hypothesis testing in Excel. Okay. If you didn't watch that video on Friday, I strongly encourage you to go back to it. It looks at how you do hypothesis testing examples by hand and in Excel for the difference in population means when we know the population variance. So up to this point, we've been using the standard normal distribution for our two population examples. On Wednesday, after we do some Excel work, I'll kind of show you how do we do the difference in sample means when we only have sample variances, which will be how, using that student T distribution. Okay. So throughout the afternoon, I should be getting grades updated. Please don't email me about kind of grade stuff until after 5. I can guarantee by then everything should be uploaded and everything should be showing up to you correctly on campus. Okay. All right. I will see you guys on Wednesday.